Excellent. So welcome Jeremy Gibbons, who's spent a lot of his life making life easier for programming in the small. So I'm gratified that he's turned his attention to programming in the large, and I expect great things. Go ahead.
Right, thanks, Mike. I hope I live up to your expectations, because indeed this is not what I normally do, perhaps. But so there's this wonderful XKCD cartoon showing the movie character interactions, and there's one for Lord of the Rings that shows all the different parties, the Fellowship of the Ring and so on, and Star Wars and Prime is down here, but Lord of the Rings is the one I want you to focus on. If you've read the book, and I guess also the movies, but if you've read the book, I remember that it was formative years for me, and it follows this group of characters, and they split up and they go off and do different things, and then they re-merge, and this XKCD cartoon shows how they interact with each other, and how the parties, so here's Boromir joining them, and then it's the end of Boromir at that point, so if that was a spoiler, but the parties split and go their separate ways, and it can be helpful to see this in order to understand what's going on, but that's absolutely not how the story is told. And the story is told from the perspective of one of these parties following along their path, their destiny, and then cutting to another one of the parties. And so the book is split up, and you spend quite a long time following one set of characters, and then you, meanwhile, back at the ranch, you go and cut to another set of characters. And that phrase, meanwhile back at the ranch, is, I mean, it's a cliched caption from silent movie era westerns, but it's become a slogan for movie making, and Hitchcock used it as, so Hitchcock said this is a good piece of storytelling advice. You want your story to be split up into several parts, and you focus on one part for a while, and maybe when that bit gets boring, or maybe more importantly, when that bit reaches a cliffhanger, you cut and you go and tell another part of the story. And I think it's a metaphor for software architecture as well, because we want to tell the story perhaps out of chronological order. We want to follow one part of it and explain how that goes, and then say, meanwhile, back at the ranch, here on the server, something else is going on. And you don't want to have to keep cutting backwards and forwards to say what all those individual parts are. So I had some work, which is kind of small-scale things, but I saw the call for papers for functional software architecture, and I thought that sounds cool. And I'd like to make the case that this particular gadget that I've been working on has applications here. So let me see if you buy that case. So now another story. Meanwhile, back at a different branch, 1972 is it? This book. The picture's not very good, but it's the structured programming book by Dahl, Dijkstra, and Hoare. And so Dahl, Dijkstra, and Hoare each have a chapter. A part of this book. And Tony Hoare's chapter, among other things, is the one that incorporates this quotation. There are certain close analogies between the methods used for structuring data and the methods used for structuring a program that processes that data. The shape of our computations follows the data that they process, and that's the motto by which I live, and all this stuff about data type generic programs and functors and categorical structure, algebraic structure in programs. That's all foreseen by Tony 50 years ago. He didn't see it in quite the same way, but it's a message that persists, and I think it's absolutely the right way of thinking about programs and where do they come from. Around about the same time, I think it's 1976, there's this book by Michael Jackson, the other Michael Jackson, called Principles of Program Design, which was about what it's not, he didn't call it this, of course, but now Jackson Structured Design, this design methodology for structured programming. And he says again, the central theme of this book has been the relationship between data and program structures. The data provides a model, and by basing our program structures on the data structures, we ensure that our programs will be intelligible and easy to maintain. And so you sketch the data, and to some extent, you don't need to explain anything more about the program. It just does the obvious thing with that data structure. And that was there's a quote from Fred Brooks about, I mean, show me your code and I will be confused. Show me your tables, your data, and I won't need to see your code. It'll be obvious. So function follows form again, except that it doesn't always work. And also in Michael Jackson's book, a large part of the book is about what he calls boundary clashes, what's also called structure clashes. So these are when your data is inconveniently in different formats. So in particular, when the input data is in one format and the output data is in another format. So input data is arranged one way and output data is arranged another way. So input data is arranged by character following their storylines, and output data is arranged chronologically, the timeline of all the movie characters. And what do you do for your program then? Well, you can't follow both of those structures. You have to pick one somehow. You have to reconcile those differences. And so that he has examples. A lot of the examples are sort of regrouping stuff. So where you have a long piece of text split up into punch cards of a certain width, and you want it in punch cards of a different width, then you need to sort of take you can't just follow the punch card structure directly. You need to sort of take it into a sequence and then take it out again to sequence broken up into different sized chunks. So the intermediate structure, the sequence structure, is not the input structure, it's not the output structure, it's something else, because these disagree, and you have to come up with some way of reconciling the two. Or alternatively, you have some stuff that's row-oriented and some stuff that's column-oriented, and one program structure doesn't give you both of those. So you might need to transpose half of the data to get it in the right arrangement, so that then you can do some nice data structure oriented, the data structure determines the program structure, zipping two things together. And I think lots of software is like that. We can't always follow the ideal view of the data structure is all there is, and you just turn the handle, the program structure matches it. Sometimes there are messy, awkward mismatches that we need to reconcile. So that's my story. What do we do when we have these structure clashes? And I argue that you want to separate, in many cases, not always necessarily, in many cases you want to separate the specification of a computation from the execution of it. So I'd like to, well, explain what these set of characters do, and then separately explain what those set of characters do, and then set them on their way, and time evolves, and you get the XKCD timeline chart. So I have one of those gadgets, which I'm trying to sell you, a data type that allows you to separate the specification of a computation from the execution of the computation, which I'll tell you about. It turns out to be an applicative functor, which is kind of like a monad. It's a way of capturing effectful computation in a pure language. I'll try to skim lightly over that because I'm not assuming everybody has seen that and knows what it is, but think of it as a representation of computations. And I'm going to start off by showing you two-phase computations, and then we're going to generalize that to multi-phase computations. And it turns out that the two-phase ones we can make heterogeneous in the class of effects. So the first phase can use one class of effects and the second phase can use a different class of effects. Whereas the multi-phase one is going to have to be homogeneous. They're all going to have to use the same class of effects. So that's rather like pairing and lists. So pairs, the type of pairs, you can have heterogeneous pairs. The left-hand component of the pair can be a different type of the right-hand component of the pair. Lists are just iterated pairing. So cons is a pair, and you just recurse in the right-hand component, and you get lists as we're familiar with. But when you do lists that way, you typically make them homogeneous rather than heterogeneous. I'm going to show you some toy examples, which I hope will be motivating and convincing examples for the gadget. And then I'm going to end up with some conjectures about functional software architecture and thinking about multi-tier, three-tier architectures and so on, but particularly thinking about choreography. So I was inspired by the Haskell paper. That's why I'm here, it's because of the Haskell paper. So a lovely paper and well-deserved Distinguished Paper Award. And a nice talk again. So I read the paper and I thought, oh, I could do that, and it fits this pattern. I think, I confess, I haven't actually done it. So this is kind of a sales pitch for collaborators, perhaps. So here's some Haskell. There's this class of applicative functors. So again, just think of notion of computation. There are two components to the interface. There's this pure and the asterisk in angle brackets, which is a kind of funny application. So think of F, the type F of A being computations that have some class of effects and return a result of type A. So they might be I/O computations or non-deterministic computations or mutable state computations or whatever. So pure is a way of turning a plain ordinary value into a computation that is allowed to do effects but doesn't actually do any effects and just returns that value. And the funny apply is a kind of sequential composition. It's a sequential composition where the left-hand part might have some effects but then yields a function. The right-hand part might have some effects and yields an argument to that function. And then you apply the function to the argument and you'll get a result. Collecting the effects from the left-hand side and the right-hand side as you go. So you might think of the pure as being a kind of skip and the funny apply as being a kind of sequential composition, and these are monoidal. So sequential composition is associative, sequential composition is the epitome of associativity, and skip is the neutral element. So that's a good metaphor to have in your head. And then there's, on top of that, there's a notion of traversable data structures. So traversable data structures are data structures where you can go over all the data structure and visit every element. So they're container data structures, they have elements in. You can visit every element with a function, an effectful function. So the elements are of type A, you can turn them into things of type B, but you might incur some effects when you do so. So maybe you turn A's into B's and using some I/O to do that. And if you can do that for each element, then you just do it for each element in turn on your tree of A's or whatever it is, and you'll get a tree of B's, but incurring a whole bunch of effects as you do. And again, there are some sensible, the laws to make sensible instances of these, but just think, go over a data structure and visit every element precisely once. You can do it in arbitrary order. This doesn't constrain the order, but you have to visit every element and you have to do so precisely once. So for example, here's how to traverse lists. In Haskell, I should have written square brackets for that. That's the list functor. To visit all the elements in the empty list with this body F, well, there are no elements in the empty list. So what you return is the empty list, but you do so, that's just a value, it has to be a computation, so you use pure to inject that. And to visit all the elements in a non-empty list, well, this is going to do it left to right, so it's first going to visit the head, and then it's recursively going to visit every element in the tail. And the interface here for applicatives is Connor McBride and Ross Patterson's interface, and it's very carefully chosen so that it looks like application, and you can write things that are just kind of application written in a different color almost. So you visit the head of the list, you visit every element in the tail of the list, and you put the results together with list comms. So this is almost like writing map over lists, and this is how you would write map over list, just with some extra bits scattered across the top, really. Now, here's a different data type, trees. So my trees here are general rose trees, they're sometimes called. It has a root label and a list of children, and each child is a tree. So it consists of an element and a list of subtrees. And so here's a tree with root label 3 and 2 subtrees. And you can traverse that too. So you can traverse it, and I'm not requiring you to do it in a particular order, but here's kind of the natural order. You can traverse this tree depth first. So there's only one kind of tree, nodes, so there's only one case for the traverse function, and you traverse the root, you traverse each of the children in left to right order, and then you put the results back together again with the node constructor. So actually what's going on here is this traverse, what's that? There are trees and there are forests. A tree has a forest of children and a forest is a list of trees. They're mutually recursive data types. And so the functions on them are typically mutually recursive as well. So here this is traverse over trees and there's traverse over forests. And traverse over trees calls traverse over forests, and traverse over forests calls traverse over trees. They're mutually recursive too, following the data structure. So following Tony, following Michael Jackson, this function follows the structure of the tree data type. So this is a recursive call. This visits every tree, every subtree using traverse, does it for every element of the list. So that's list traverse is the outermost one. So for each element of the list in some order, we're going to visit all the elements of that child. Now, which order we're going to get for list traverse? It's the one we specified when we specified list traverse. But perhaps you can see, if you do this, you'll visit the root, and then you'll visit everything in the first child, and then you visit everything in the second child, and so on. So this will be a depth-first traversal over the tree. And this is so straightforward, so determined by the data that you don't have to write it at all. You can get GHC to derive it for you. But that's depth-first traversal. What about breadth-first traversal? That doesn't work nearly so nicely because, so to speak, it cuts across the grain of the tree. And so I've spent some time in my life thinking about breadth-first traversal. My first ICFP paper was about that as well, a long time ago. So that's a cliffhanger. Meanwhile, back at the ranch, I'll have a drink. So here's another problem, and this is one due to Richard Bird. And it's called the rep-min problem, and it involves taking a tree, finding the minimum element in the tree, and replacing every element in the tree with that minimum element. So this computes the minimum element of a tree. This does the replacing of a tree, every element of this tree by this value. A minimum, there's something for minimum of trees, a minimum of forests, a minimum of trees calls minimum of forests, a minimum of forests calls minimum of trees. Same pattern again. Replacing on trees, replacing on forests, replacing on trees calls replacing on forests, replacing on forests calls replacing on trees. The same pattern again. Those both exactly follow the structure of the tree data type. So, but the tricky thing is you're supposed to do this in one pass rather than two passes. You're not allowed to go once over the tree to find the minimum element and then a second time over the tree to do the replacing. So Richard used this in a paper in 1984, I think, arguing for lazy valuation and letrec and in your language, because there's a nifty cyclic functional program that does it in one pass. Now, whether it actually does it in one pass, I'm not going to get into that. And you might argue, I think you might reasonably argue about whether it's doing anything any better. And it's true that it's not any faster than doing this. But here's Richard's program. There's an auxiliary function, and again, one for trees and one for forests, and they're mutually recursive. The auxiliary function takes a tree of integers and some replacement thing of some arbitrary type A, and gives you back the minimum in that tree of integers, which is an integer, and then another tree of the same shape that you first thought of, but with this a value instead of the ints that you started off with. And because min t and replace t both follow the shape of the tree, they have the same shape, so these two computations can be fused into one. One is sometimes called the banana split theorem. They're both folds over the tree, they both follow the same structure, and so you can write one fold that generates the pair of results. And that's exactly what's going on with this orgs function here. So there's no magic in the orgs function. It's just the thing you would easily write that does both the minimum and the replacing in one go. And no cyclic, nothing fancy here. The only clever bit is the first line, because what we want to use the orgs function for is the replacement value should be the thing that we could compute as the minimum. So that's done with this let. Orgs t produces a pair um, and that m is also the input to the function. So this let is a let rec. It only works because of that. You're allowed to have that cyclic dependency, and it's not actually cyclic. And you can verify that by seeing that, let's see, the int that comes out here is independent of the a that went in. In fact, even from the type of the polymorphic type of orgs t, it's apparent that the int can't depend on the a because there's nothing you can do with the a if it's polymorphic. So even if you don't know what the m is that goes in here, you will get a sensible m out, and therefore it's productive. So you will get some m to feed in. So that was Richard's paper in 1984. He is a bit before my time, but he must have talked about this at IFIP Working Group 2.1, which is the squiggly program transformation calculation kind of working group. And Alberto Peterossi, who's also in that group, I infer, heard the talks and said, yeah, you don't need to do that. Here's a better way of doing it that doesn't involve laziness. So the difference is rather subtle. Watch this type here for orgs t. This one takes a tree of ints and produces the minimum as before, but produces a function as the other thing, which is the dependency between the output tree and the input replacement value. So it's computing a higher order. It's a higher order function. It computes the function as a result, as one of the two components of the pair that it returns. So you call orgs t, and you get two things, but now m is the min as before, but u is a function, and you apply u to m. And the call of orgs t is not circular anymore. And so you don't need a let rec, you can just do it with a let. And so Alberto said you don't need all this fancy lazy stuff, you can just do it with higher order programming instead. I mean, to my shame, I didn't know this. I know Alberto very well, and I've been a member of 2.1 for donkey's years, and this is not widely known and not widely cited. It doesn't help that it's published in obscure places, but Richard's example is a kind of a canonical example of lots of program transformation, program calculation papers. So what's going on here? What's the relationship between these two? Well, I'll tell you that story as well. And what these have in common is about traversals. So if I have, so now this is another operator. It's a pairing, a kind of zipping operator on effectful things. If I have a computation that returns A's and a computation that returns B's, I can, in a sense, run one after the other and get a computation that returns A-B pairs. So if I have a traversal that produces a tree and a second traversal of the same tree, so the same shape of traversal, combining, so one traversal uses F on every element, the second traversal uses G on every element. Can I do that? Can I fuse those two traversals? Can I do that in one traversal rather than two? So can I do it with a single traversal that does F and then G on every element? And that will give me a tree of pairs, and what I want to end up with is a pair of trees, so I have to do some unzipping afterwards to make the types match up. Can I do that? No, obviously not. If you do the left-hand side, traverse the tree everywhere and do F on every element, and then traverse the tree and do G on every element, you'll get all the F effects before any of the G effects. Whereas the right-hand side interleaves the F and G effects. So obviously, in general, those are going to be different. Now, if the class of effects is a commutative class of effects, so if it's reading from a context or probabilistic choice or something like that, you don't mind the interleaving. You can't observe the interleaving. And so you could say those two things agree. But that's very restrictive. You can't do I/O, you can't do stateful stuff. So that's not a very satisfactory answer. So even if the class of effects is not commutative, if the actual effects that F might yield and the effects that G might yield do commute, then you can still do this fusion. So imagine F working on mutable state, G working on mutable state. Mutable state is not commutative, but F works on the left-hand components of a pair that's the mutable state, and G works on the right-hand components of the pair that's the mutable state. They will not interfere with each other. They will commute in this, according to this equation. And in that circumstance, this traversal fusion theorem applies. So in particular for us, when the class of effects is multi-phase computations, and the F says do things in phase 1, and the G says do these things in phase 2, those will commute. So if I tell you do X now and do Y later, that's the same as telling you do Y later and do X now. Either way, you will do X then Y. But my specification of what you should do will commute, even though the execution will not. So how can we capture this distinct phases thing? And the trick is what's called day convolution. So F and G here are think of them as applicative things, classes of effect. So this is a day FGA is a representation of two-phase computations. The first phase will do some stuff and get effects of class F. The second phase will do some stuff and get some effects of class G. Now to make it a functor where you've got different things going on here, there's a trick that says, well, let's pair that up with something that takes an AB pair and produces a result of type C. It's now trivially a functor because if you've got one of these and you know how to turn C's into D's, then you make one of these with a D instead, because you just stick the C to D function in the post processor here. So that's called the co-Unada trick, parceling up some complicated gadget with a post processor, a simple post processor, and then you can do simple things to it by doing them on the simple post processor.
Why is it called Day?
Why is it called Day? Because it was invented by somebody called Day. And it's called Day convolution because it's something to do with convolution in the sense that goes over my head. It's a category theory paper from 1970. But yeah. And if F is an applicative functor and G is an applicative functor, then day FG is an applicative functor. So I can think of this as a class of effects. So I'm going to use that for my two-phase computation. So if I've got something that returns a result of type A incurring effects of class F, then I can make it one of these two-phase things that just skips in the G phase. So this is the I haven't shown you this, but this is the pure unit for the G phase, and then I've got some A's from the F phase, and I post-process them by discarding the units. And similarly, if I've got a G computation, I can make it into a two-phase computation with a trivial first phase. Crucially, the phases commute. So to do X now and do Y later is the same as do Y later and do X now, as long as you post-process the results properly. And if the two classes of effects are the same, do X now and do Y later, and they both collect effects in the same applicative functor F, then I can just run them one after the other. and I'll get something that's again in the applicative functor f. So for example, this is the applicative funny apply, but discarding the left-hand argument, which is fine here because it just returns void. In phase 1, say hello. In phase 2, say world. Off you go and do it. It says hello world, as you might expect. In phase 2, say world, and then in phase 1, say hello, and then go off and run it. You also get hello world. Those two things commute. And you can even interleave the bits. So phase 1 hell, phase 2 world, phase 1 low, and again you get hello world. So this is the meanwhile back at the ranch. You can tell part of this story, then go off and tell the other story, and then tell, the things will come out in the right order. So I think this is a bit like literate programming. So this was what Knuth came up with to, well, he had this story in 1984, I think, paper in the Computer Journal, and then a whole bunch more papers that were collected in a book, saying if we want to have good programmers, we should be talking to them, explaining to them how to write good programs. We shouldn't just say, here's the syntax, off you go and do it. We should say, here's a good program and here's why it's a good program. We should narrate it, explain it. We should write essays about programs. And lots of us do this. But in particular, he was thinking about writing Pascal programs, and the original version of Tech was written in Pascal. And Pascal is a very restrictive language about the order in which things must be stated. So it has constants and it has type declarations and variable declarations in it. And in a Pascal program, you need all the constant declarations need to come before any of the type declarations, and all the type declarations before any of the variable declarations. That's to allow a one-pass compiler, which was important in the machines of the late 70s. But you don't want to write your program like that. You've got one data structure that's got some constants and some types and some variables, a table of some kind, and then you've got another data structure that's got some constants and some types and some variables, a tree of some kind. You want to say, here's my table, blah, 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 blah. Here's my tree, now put them together into a program, get all the constants and all the types and all the variables, and the order in which the compiler sees things is not the order in which your essay presents them. So that's very much like the argument I'm trying to make. And similarly also, you might see this in program generation, metaprogramming frameworks like Halide, which is, to read this, there are just to show you, there are some pretty pictures. Halide generates array, two-dimensional array processing code, so image processing code, by separating the algorithm, the declarative specification of what's supposed to happen, like matrix multiplication, from the scheduling, which in order to get cache coherence and so on, you need to be very careful about blocking and strides and all kinds of stuff. So you don't want to write those but all in one program. You want to say something simple about sums and products for matrix multiplication, and then something separate about scheduling. And I think that's also, I claim that as within my, the umbrella I'm aspiring to put up. So let me try and justify my points. I'm going to use, in Haskell, two monads, but the monads, they're not applicatives, but that's fine because every monad is an applicative. Retmin, the essence of Retmin, the core of Retmin, is a two-phase thing that in the first phase goes over the tree and writes out the minimum value and collects the minimum value, aggregates the minimum value. And in the second phase goes over the tree and reads from the context, and that's going to be the minimum value. So I've got one function that does this, and this is the function. In phase 1, I'm going to go through the tree and write out the minimum value. And in phase 2, I'm going to go through the tree and read that copy. But one of the laws about traversal is if you have a morphism of applicative functors, it will commute with traverse. What do those words mean? Well, there's transforming one applicative functor into another applicative functor in a disciplined way. That's a morphism of applicative functors. And it turns out that phase 1 and phase 2 are such morphisms, which means to say in phase 1, go over this tree and do this, is the same as to say, go over this tree and for every element in phase 1 do this. It doesn't matter, the phasing and the traversal don't interact because traversal is pure, it doesn't actually do anything. And now I've got a traverse with a phase 1, and then a traverse with a phase 2, and phase 1s and phase 2 commute, so I can fuse those two traversals. And I have manifestly a one pass traversal over the tree. There's only one pass in the code. Then Richard's Retmin solution uses this Retmin awks with a writer thing and a reader thing, and just extracts the writer thing and the reader thing in one go, and post-processes the result, but does so necessarily using a letrec because, well, let's see here, the S that you want to run the reader on is only obtained from the writer part. So that let needs to be a letrec, but that's all you need to do to the Retmin orgs to get Richard's solution. And Alberto's solution is not to extract those two things in parallel, but to extract them one after the other. So unpack the abstraction of the writer thing, you'll get an XS. Unpack the abstraction of the reader thing, apply it to S, you'll get a Y, and then you can post-process the X and the Y. And those lets do not need to be letrecs. So and as lazy programs, as Haskell programs, clearly let X equals A, Y equals B in something is the same as let X, Y be A, B in that something. What could be more equal? And so the explanation of what's going on really is this two-phase thing, this day convolution. Now you can do the same with multiple phases, and it's just an iterated use of this day convolution. So this is like the day convolution construction here. In fact, I could have used day convolution for the link. So there's a nil, and there's a cons, and this is a chain of phases with some post-processing. A homogeneous iteration of day convolution. It's an applicative functor. In fact, the data type is the data type for one of the data types that gives you the free applicative, but it's not the same applicative instance I'm going to use. I'll skip over that because I haven't explained all the constructions. But so what the free applicative will do is to pair things together. It will do all the first things and then all the second things. But what we want to do, where we say here is some stuff for different phases, and here's some more stuff for different phases, you want to zip them together. You want the phase 1 things to combine with the phase 1 things, the phase 2 things to combine with the phase 2 things. And then you can inject a two-phase thing into a multi-phase thing. You can inject a thing into a multi-phase thing at an arbitrary phase. And you do that by having a now or a later. So again, don't worry about the code, just let the ideas wash over you. Something that's more than two phases, here's a kind of artificial thing that's more than two phases. Also in Richard's papers and Alberto's papers about the cyclic and the higher order programs, is to sort the leaves of a tree. So one pass, you go over the tree and collect all the leaves, that's the list. Second phase, you don't touch the tree, you just sort the list. And third phase, you go over the tree again and distribute the elements from the list across the tree. And then you'll have a tree with sorted leaves. But you want to do it in one pass, not two or three phases. So this is the program. In the first phase, you collect all the elements. The second phase, you don't traverse the tree, you don't touch the tree, you just sort the things that you've collected, and then you traverse the tree again. But you can do the same kind of calculation before the phases commute. So let's put the modify sort in phase 2 at the beginning. Then we've got phase 1 traverse and phase 3 traverse, and they'll fuse into one traverse. And so you've got this program down here. which is manifestly a single pass because there's only one occurrence of traverse in it. And that will sort the leaves of your tree in a single pass. And here's the breadth first traversal, the other story I left you with. Here's the traverse I gave you, the depth first traverse I gave you, except I just called it DFT for depth first traversal here. And all you need to do is stick a now for the root label and a later for the children, and you'll get breadth first traversal. It's only a matter of aligning the phases appropriately. So I have a whole bunch of complicated earlier programs over the last 25 years for breadth first traversal. This is much simpler than any of them. I didn't know about applicative functors then. So what has all this got to do with anything? As I said, it was the Haskell paper, Lindsay and Gan, and your co-author, who I can't read in the picture. Jun, thank you. Made me think, well, can I do the same kind of thing? You use free monads for representing the global program, and then you just kind of parse those free monad things in different places, different ways for different locations in the network. So endpoint projection is a matter of taking the free monad program and saying, well, what does the client do? What does the server do? They just interpret this common program differently, and that's very sweet. But I think it's doing a phase distinction. So what's different is the things I've shown you. There's a phase 1, there's a phase 2, there's a phase 3. The phases are indexed by natural number. In retrospect, I should have gone 0, 1, 2 rather than 1, 2, 3. But there's nothing inherent about the numbers, and I'm not doing any arithmetic on the numbers. And I might as well have phases indexed by location, I think. So there's a phase for the client, and there's a phase for the middle tier, and there's a phase for the server or whatever. And I say, here's what to do for client, middle tier, and server, and then here's some more stuff that happens on client, middle tier, and server. And the whole thing is put together. So, I mean, whether it's tiers or whether it's parties in a distributed message protocol, I conjecture that would all work. As you saw with the repmin, you can use monadic things in a given phase. So you can do monadic things in, I had the reader and writer monads. You can have monadic things in phase 1 and monadic things in phase 2. That's fine because every monad is an applicative. You only get an applicative structure, but I think that's, this was a question that I would have asked if Alan Jeffrey hadn't already asked it after your talk, Gan, about the dynamic versus static. And I think, correct me if I'm wrong, in Haskell, the endpoint projection happens dynamically, and earlier parts of the protocol, of the choreography, might change what gets projected, which gives you great flexibility, but seems contrary to the spirit of endpoint projection. And it's not how everyone does endpoint projection, I think. So the book by Fabrizio Montesi has endpoint projection as a separate phase. It's something that happens statically. And this, doing it with this deconvolution multi-phase thing, I think would give you transparently a static division. And then I think Alan also asked about conditionals and the selective, applicative, and so on. So maybe I'd love to keep talking. So I'm going to conclude. I did, in fact, use my time. There's a paper from Maths of Program Construction 2022. It's joint work with Oisín Kidney, Tom Schrijvers, and Nick Wu. And I encourage you to read it. It's on my webpage, or it's open access at Springer. I think choreography is an applicative thing, and I think this deconvolution, this multi-phase thing is the way of capturing it, and multi-tier stuff and so on.
Thank you. We can do one quick question, I think.
You said that phases could not be numbers, but something else,
Right.
like locations. But the phases are ordered in somehow.
Well, if I'm going to want to run them one after the other, then I need to say what order I'm going to run them in one after the other. If I don't want to do that, I don't need to do that. So if I say there's a client phase and a server phase, and then I end up with this thing with something for client and something for server, I need to then extract the client stuff and the server stuff. And I just say, well, the client stuff goes to the client, the server stuff goes to the server. And then hopefully, I mean, as in a choreography, they will run concurrently, not one after the other. So I can use natural number indices to schedule these one after the other, but I can use location indices to schedule them by distributing them to different sites. So it doesn't have to be one after the other.
Well, we can do one more.
You baited us by saying that maybe this is not really one traversal, but you won't go into it.
Yep.
Was it a bait that you want us to ask you about, or?
Well, I mean, I think it's indefensible that it's really saving you anything, and it's actually very obvious in Alberto's program that what you construct in a single pass is the minimum and a function. And that function is a closure that contains all the structure of the tree because it's something that takes the replacement label and gives you a whole tree. So now I give you the replacement label, you have to unpack it to a whole tree. So, I mean, you're not traversing something, perhaps, but you've still got a whole tree's worth of stuff to do.
Is there a solution where you're not creating a hidden tree?
Well, I've argued with Nick about this and what's actually going on, and you write it in different ways. I mean, it just messes with my head. I don't know what's going on. So you might say you end up with one pass over the tree, you get the minimum, and lots of shared pointers to the same. In the same pass, you make a new tree that has lots of same pointers, shared pointers to the same thing, and then you just fill in that thing like a logic variable. Is that actually what's going on? Well, I deliberately don't think about those questions. I have no operational model, really, of what's going on with my Haskell code. I deliberately have an equational model, and I can only stay sane by only focusing on the equational model. And then Nick comes and has an argument with me and says, no, it's not doing that. And I think, oh, poof.
If the spine of the tree is strict, right?
Yeah.
In the lazy version,
Yep.
And you just have a lazy cell where the
Yep.
minimum goes, then I think you can get
Right.
away with one
I
traversal.
certainly think you can get away with that. Whether these programs actually do that, I don't know.
Yeah.
Yeah.
All right. Thanks. And there's a break now.